Combustion efficiency. What is combustion efficiency? Well, combustion efficiency is the measurement of a furnace's combustion quality, which is essential in its ability to achieve complete combustion. Incomplete combustion can occur when we have a loss of flame temperature, when we have carbon monoxide, or when we have reduced heat transfer in the heat exchanger. The best to test the furnace combustion efficiency, a technician has to follow and take a couple of measurements and a couple of variables in order to see how a piece of equipment actually is operating. We need to take into effect its carbon dioxide content. We need to do oxygen. We need to take a carbon monoxide reading. We need to also take gas pressure. And we need to check the temperature of the stack or flue pipe. When we're dealing with the carbon dioxide content, it's the measurement of a percentage of the total flue gas being vented to the outdoors. We use a combustion analyzer to measure carbon dioxide content, and then to measure that carbon dioxide content, that analyzer sensor is put into the flue pipe or your vent pipe. In addition to measuring carbon dioxide content, we have to be able to measure other variables such as oxygen, carbon monoxide content, and obviously stack temperature. All three of these play a vital role in figuring out whether or not a gas furnace is operating efficiently. Ultimate carbon dioxide content is the specific amount of carbon dioxide by volume that is present in flue gas when the exact amount of air is supplied to achieve complete combustion. Now, for natural gas, we are looking at, in order to achieve complete combustion on that type of fuel, we are thinking about that we have to have about 11.9% carbon dioxide content in order to have complete combustion of natural gas. For LP, we're thinking about around 13.9 carbon dioxide content. Now, however, the values of these are going to change based on the amount of excess air that the furnace does actually take in to ensure complete combustion. So we have to keep an open mind with the numbers that we are technically seeing. The excess air dilutes the amount of carbon dioxide by volume in the flue gas. So as a result of this air dilution, the carbon dioxide content in natural gas honestly is a lot closer to about 7.6. That is more realistic in terms of combustion efficiency. Remember, you have complete combustion and you have practical combustion. When we're thinking about those two, which one is more likely to occur? We're going to have more likely of a practical combustion. Okay, we have to take into account the actual room area that this piece of equipment is sitting in. So roughly as a rule of thumb, when we're taking a combustion efficiency reading, we're looking somewhere more around the lines of 7.6% for carbon dioxide reading on our measurements. LP, obviously, since LP is a little bit of a heavier gas, that carbon dioxide content is going to be a little bit higher. So for practical combustion, we're looking at somewhere around 8.9%. With oxygen, both natural gas and LP gas, the percentage of oxygen in the flue gas should be anywhere between 6 and 9%. Those are pretty much a given rule when it comes to the efficiency of a furnace. We're looking for somewhere in between those numbers. Usually, we're going to run into about 7.5% oxygen. If you have anything less than that, you obviously have an issue with the combustion air in the room. You may have to consider putting in a makeup air vent or some sort of device to bring in some additional air to help support combustion. Okay, this both holds true for condensing and non-condensing furnaces. Our carbon monoxide content. The presence of carbon monoxide in a flue gas is a direct measurement of the quality of combustion. Okay, excess carbon monoxide production indicates that there is obviously incomplete combustion. According to the American National Standard Institute, the maximum concentration of carbon monoxide permitted in a furnace flue gas is 400 parts per million. However, many manufacturers do specify that a concentration greater than 50% parts per million obviously will indicate a problem. Now, when it comes to carbon monoxide, you're going to have carbon monoxide no matter what. Okay? We want to keep that carbon monoxide content as low as possible. The lower, the better. Now, like it says, according to the National Standard Institute, yeah, we can have a maximum concentration of 400 parts per million, but in reality, I think that's a little bit high. We want to try to keep it down. Okay, try to 150 parts per million, you're good. If you are having issues with the carbon monoxide, you need to start inspecting that heat exchanger and seeing what's causing it. Although the correct percentage of carbon dioxide, oxygen in the flue gas is vital to determining carbon efficiency, the correct percentage only indicates complete combustion if there is no carbon monoxide being produced. Okay, so for example here, in a natural gas furnace, the flue gas can have a carbon dioxide content of about 6.7%, an oxygen content of about 9%, and a carbon monoxide content of roughly 200 parts per million. These values are relatively close to the desired values. However, the carbon dioxide content is low and the oxygen content is high. So the presence of carbon monoxide is most likely an indication that there is too much excess air. Okay, too much excess air decreases our flame temperature and allows some of that carbon monoxide molecules to pass through the combustion zone without actually burning. Okay, remember, go back to that combustion triangle. We got to have enough air, we got to have enough fuel, and we got to have enough heat in order for us to have a complete burn. If one of those three is off, you're going to have an incomplete burn and you're going to run into issues. So if the carbon dioxide content is high and the oxygen content is low, the presence of carbon monoxide may indicate that there is a leak, a lack of air to mix with the fuel. Okay, so acceptable amounts of combustion products in a flue gas. This chart here is really important. If we're dealing with a natural gas, we are looking at CO2. We're looking at somewhere around 7.6% LP, about 8.9%. O2, ideally for natural gas, 7.5%. Same goes for LP gas. Our CO, we are looking for less than 50 parts per million for carbon monoxide on any reading that we're taking. If you have anything other than that, you got an issue. Okay, gas pressure. Gas pressure is another factor that can affect a furnace's combustion efficiency and cause the production of carbon monoxide. An increase in gas pressure can cause incomplete combustion simply due to the lack of air to mix with the increased amount of gas. Okay, increased pressure can also lead to similar conditions as lack of air, high carbon dioxide content, and low oxygen content. A decrease in gas pressure decreases the flame temperature and can lead to similar conditions as too much excess air, low carbon dioxide content, and high oxygen content. Okay, so what we're really getting at here is that we have to make sure that we are giving enough air to the furnace. We are making sure that we have to have the proper gas pressure. All of those will coincide with each other. Okay, a technician all the time when he is doing a combustion efficiency test should be taking gas pressure measurements to make sure that it is not the cause of any problems with the efficiency of the furnace. Okay, gas pressure is measured obviously in inches of water column. Inches of water column is used to measure pressure above and below atmospheric pressure. So about 28 inches of water column will equal 1 psi of pressure. With natural gas, we are looking at a manifold pressure of 3.5 inches of water column. LP manifold pressure about 10.5 to 11 inches of water column. Okay, those are pretty standard. Our stack temperature, which is also called net stack temperature, is the temperature of the flue gas in the flue minus the temperature of the combustion air. Okay, when we hear minus the air combustion air, we're thinking about the temperature of the room itself that this furnace is in. Okay, so when combustion air enters from the furnace room at room temperature, stack temperature is essentially flue gas temperature minus room temperature. When combustion air is drawn from the outside, the temperature is colder. So flue gas temperature minus your combustion air temperature will give you your stack temperature. So stack temperature is directly related to the amount of excess air and inversely related to the furnace's efficiency. As excess air increases, a furnace's stack temp also increases, and the efficiency will decrease. This is because the increased excess air carries more heat through the flue to the outdoors. The increase in stack temperature indicates that less heat is being transferred in the heat exchanger to the circulated air through the ductwork. Less excess air and low stack temperature will equal a more efficient furnace. Okay, so there is your key to getting your piece of equipment at a much higher efficiency. Less excess air and lower stack temperatures. Okay, so this is an example of what we're talking about here. So say we have a furnace that's running at about 9.5% air, 2% oxygen, and we are running at a net stack temperature of roughly 300 degrees. That furnace would be running as precisely or approximately 83% efficient. Okay, now if we were able to lower the stack temperature to say around 200 degrees, that furnace would now raise its efficiency to about 85.5% efficient. Okay. In general, there is about a 1% decrease in efficiency for every 40 degrees increase in stack temperature. Okay, the stack temperature in non-condensing furnaces should be anywhere between 325 and 500 degrees. Condensing furnaces should be less than 140 degrees. BTU input is measured by clocking the gas meter, the number of times the dial goes in 1 minute, and then multiplying the number of revolutions by 60. The result is now in cubic feet per hour. So multiply the input by the efficiency percent to find the output. Now, if the firing rates are too high or too low, this means that the input is not where it should be. Okay, this could be caused by incorrect orifice sizing or incorrect gas pressure. Look at your manufacturer's literature, look at the nameplate to see what your pressure should be and what the actual orifice size should be. When we are also checking our firing rates as if they're whether too high or too low, we are going to definitely be checking that gas pressure. We can use a U-tube manometer or some other type of manometer to check our gas pressure. Again, normally we're looking at 3.5 inches of water column for natural gas, 10.5 to 11 inches of water column for propane. If the pressure is correct or it cannot be corrected to fix an overfiring issue, then we are going to look at the orifices. We are going to make sure that the orifice sizes are correct, and if they are not, we are now going to reduce them in size. We can go down the next size down, and then take another firing rate calculation to see whether or not we are actually more within the range of what we need it to be. Okay, fixed orifices are sized by the specific gravity of the gas that we're dealing with. They are sized by the manifold gas pressure. They are sized also by the altitude in which the furnace is sitting. And they are also sized by the cubic feet per hour in which that furnace is burning. So to find the correct orifice for the input, you got to first find the input rate from the manufacturer. Then you are going to divide this by the number of orifices to find the BTUs per hour. Use a correction chart for higher altitudes, obviously, if needed. You are going to find these types of charts in your National Fuel Gas Code book. This is where a lot of this information is coming from. The temperature rise over the heat exchanger must also be checked and also should be corrected when we are doing a combustion efficiency test. Okay, you're going to look at the tag on the furnace, and that will give you the correct temperature rise across the heat exchanger. That temperature rise could be anywhere between 50 degrees to 130 degrees. It depends on manufacturers. You're going to have to look at this information to see where our temperature rise is supposed to be. And if we are not within that rise, we are going to have to look at airflow. We're going to have to make sure that the blower is at the correct speed so that we can achieve the correct temperature rise across the heat exchanger. Okay, incorrect temperature rise is a symptom of problems. This can be anywhere of airflow in the duct systems may not be correct. You may have an efficiency problem, maybe underfiring or maybe overfiring. Okay, the firing rates are going to be a big factor in what is causing our furnace to not be firing within the proper range. Okay, to measure our temperature rise, you have to measure your supply and your return temperatures after 10 minutes of runtime. Reason why we say 10 minutes of runtime is because we need the system to have enough time to warm up. We need the heat exchanger to get to its highest temperature that it's going to be at in order for us to see what the system is actually doing. So to take that temperature rise, you have to subtract those two readings. So take your supply temperature far enough away to prevent the radiant heat from the heat exchanger from affecting your readings. You are going to want to take these readings probably at the first supply run that's going to go to a room, probably a flex connector or some sort of first connector on the supply duct is where you're going to want to take this reading. Do not take it right above the heat exchanger. It's going to be hotter there. You want to take it down a little bit so that the air is actually kind of diluted a little bit to get a more accurate reading of what your supply temperature is. Okay, the CFM of a furnace can be found using the temperature rise and the combustion efficiency. Okay, the formula to figure out what your CFMs are is BTUs divided by 1.08 times your temperature rise. Put in your numbers, and that will give you your CFMs. So, for example, here we have a temperature difference of 65 degrees. We figured out that the BTU per hour is 80,000 BTUs per hour. We plug in our numbers. 80,000 divided by 1.08 times 65. We come up with 80,000 divided by 70.2. And now we have a CFM of 11,139, or we can round it up to 1,140 CFMs of air is needed to be moved across that heat exchanger. We can now use a blower chart. We can now look at our blower speeds and see whether or not we are moving the correct amount of air. And if not, we can change the blower speed to a little bit higher or a little bit lower. And if the temperature rise is too high or low, make sure the CFMs do meet the manufacturer's recommendation. Or if you don't have the literature, or you can't read it, or it's missing, or what have you, you can always use the rule of thumb of 10 CFMs per 1,000 BTUs of heat.